So if we're going to look at trying to solve this question, we need to figure out what each of these things can go through and do. So where we would typically start is what's the most reactive thing? And that should be more or less not an easy question. Okay, so why? What do you see as the most reactive? Okay, so I think I heard reference to the pi bonds. Whoa, that's an eraser. I'm going to make that pi bond slightly different colored. Then I heard you say the carbon. Okay, the carbon of the carbonyl. Okay, what other reactivity do we see? Okay, that CH3SH, I'm going to draw a little bit larger. I don't know why I didn't just commit to erasing and just redrawing everything, because it's effectively what we're doing. There's our CH3RS and our H. Okay, within that, I heard someone say nucleophile, because that sulfur has lone pair electrons, so it could act as a nucleophile. Which is going to go to kind of the next question behind this, identifying the chemistry of all of these individual things. We'll actually color code the sulfur a little differently. So sulfur could act as a nucleophile because it has those lone pair electrons. Okay, so that's decent. What other stuff do we have? Okay, so that carbonyl carbon, our purple dot is partially positive, which would suggest we're looking at what chemistry? Okay, an electrophile. So we could go through and say, well, if I've got a nucleophile and an electrophile, I could put them together. Yes, we could do that, but we've got a whole bunch of other functionality present. So what we need to do is make sure that there isn't a better electrophile or a better nucleophile. Okay, so you've just identified two reactivities, but we've noticed there's other chemistry there. You got to address it all. Okay, there is resonance. What is that resonance going to do? Create another electrophile site. That's going to become important because we now have the potential for two electrophiles. If we're going to go through and look at the reactivity on those particular sites, and now I'm going to commit and redraw that structure. We've got a partial negative building on our oxygen with a partial positive building on the carbon or the carbon. So if I looked at this as a system, I could look at doing a nucleophile addition to these two spots, which would make it adding things at the 1 and 2. We're looking at a direct addition. Or if I added it, this box is going to look a little bit weird. Okay, in that direction, we'd be looking at 1, 2, 3, 4, a 1, 4 conjugate addition. Okay, before we go down that path, which, for the record, is the correct path, okay, what else should I consider before launching into that? Do I have another 1,4 addition? There's another alkene, right? Okay, it's too far for that 1,4, so that's going to be an alkene kind of chilling on its own. That's a weird green. Okay, so that alkene in and of itself is now just a non-polar pi bond chilling out there. If it's a non-polar pi bond, what would it act as? It would act as a nucleophile. So if we're considering our reagents, if we've got that sulfur up there as a potential nucleophile, are we going to be reacting with that green alkene? No, those are both nucleophiles. That's going to be off the list. So that's there as something just to mess with your peripherals and potentially screw up your interpretations. Okay? So now we've got to shift to the primary chemistry. We're looking at that nucleophile doing either a 1,2 or a 1,4 addition. How do we decide between 1,2 direct addition versus 1,4 conjugate addition? What differentiates between those?
If it's oxygen, we get the thermo. Anything with like an oxygen.
Okay, so we're going to come back to that. So you start with anything with an oxygen, we get a thermo. I haven't written thermo, so tell me what's thermo.
Conjugate addition is a fancy way of saying thermodynamic.
Okay, which then means the red one is our kinetic. Okay, and now I want to push on this. You said oxygen means?
Thermodynamic?
Cool. Are we adding an oxygen?
No. However, we're adding everything else, which is a sulfur.
Okay, there we go. So if we went through the delineation that we talked through in class, our kinetic was our hydrogen and our carbon, and our thermodynamic was our oxygen, nitrogen. What was that differentiation between those? How was that determined? There's a line that differentiates kinetic versus thermodynamic. So we could look at stability of the intermediates. That means we got to draw out a whole bunch of stuff. Do you want to draw out a whole bunch of stuff? No, so we got to look for something else. We're talking about this H, C, O, and N. What are they acting as in each of those cases? When we say O is the thermodynamic, what is the O acting as in the 1,4 conjugate addition? What is the N acting as? What would the H be acting as? There it is. Okay? In all of those cases, what we're talking about is the strength of the nucleophile. And if we had a stupid strong nucleophile, i.e. hydride or carbide, we got a kinetic product. If we just had a strong nucleophile, we're looking at an oxygen or a nitrogen, okay, giving us the thermodynamic. Does that make sense? Okay, so you've evaluated hydrogen, carbon, oxygen, and nitrogen. Where is sulfur in that list? It's below oxygen. Well, what's determining the strength of the nucleophile? Okay, has to do with how well it can stabilize that charge. So if we're looking at oxygen versus sulfur, we could evaluate based off of our charge, size, electronegativity, resonance. Okay, and ultimately what we're going to find is that sulfur can stabilize that charge better, which means it is a weaker nucleophile than our oxygen. And if it's weaker than oxygen, and oxygen is thermodynamic, what are our nucleophiles for hydrogen and carbon? Are those weaker nucleophiles? Those are stronger. If sulfur is a weaker nucleophile than oxygen, that means more thermodynamic. Okay? Which means our sulfur is going to be in this bottom case doing our conjugate addition, which means where should our sulfur attack? That fourth position, ooh, not sure what I was trying to draw there. So if we're looking at our crude drawing out, we want it to react to the fourth position. We'll put our sulfur out there with the methyl. For those people looking at it being like, but what happened? You have that double bond there. I fully get that. We aren't trying to draw the product. Why are we not trying to draw the product? Where did this question come from? Where was it found? Yes, on the exam. Where in the exam?
Multiple choice.
In the multiple choice. So what you're trying to do is say, I want it to react. I want the sulfur to react at the fourth position. Do I need to draw out a fancy product? That answer of deciding whether I need to draw it out or not has to do with what are my answer choices. And when I go through and look at my answer choices, which answer choice or choices puts the sulfur at that fourth position? A. And Does D put the sulfur at that fourth position? If we look at D, where is it placing the sulfur? It's placing it on the other alkene, right? That's not the fourth position. That's not a 1,4 addition. That's not part of the conjugation. So while D is showing the sulfur on an alkene at the terminal end, that's fine. It's not the alkene that's reactive. My notation where I'm putting the sulfur onto that fourth position of my 1,4 addition helps me to see where I want the sulfur to react. I can now look at my answer choices and say which answer choices match that. A and A. That's it. It's only A. Which means the answer is A. I don't have to work through the whole mechanism to figure this out. All I have to do is identify where that chemistry is, effectively what the question is asking about, strength of nucleophiles. That's it. Once I've got that nailed, I have the answer. I don't need to propagate through all my possible answer choices. Does that kind of make sense? Okay. And if we push through and look at the other answer choices regardless, what's happening in C?
A 1, 2.
C is doing a 1, 2. What's happening in B?
It's replacing the oxygen. Doing a whole.
So C gets a little bit harder to piece out.
Instead of weight.
That's still a 1, 2. You're still putting the sulfur to that spot, but you're doing a full replacement as if the sulfur was a nitrogen, going through that imine type fashion. Okay. B should set up alarm bells being problematic. Why?
No charge on that sulfur.
If that sulfur has 3 bonds, it should be positively charged. Okay. So it's still trying to show that 1, 2, but maybe what you've memorized with our nitrogens in those 1, 2 direct additions is that it replaces the oxygen. Okay. So we've got an answer choice that makes it look like, ta-da, you just replaced the oxygen. I mean, is it possible? Yeah, but we need to see some charges. We need to see some extra pieces. Those charges are not shown, which means our structure is problematic. At best case, we have a typo. Okay, so B would be off the map. C is off the map. Both of those are showing the 1, 2. We think it should be doing the 1, 4 because the sulfur is a weaker nucleophile. What happened in D? The nucleophile reacts with a nucleophile. So by identifying that chemistry, calling that out, that's step 1. Every time we look at a chemical reaction, what do I ask you to do? Identify the chemistry. Because if you can identify those chemistries, you can eliminate those answer choices. D still looks like a reasonable choice. But it comes down to, are you following the chemistry as it should flow? Kind of makes sense? Why does which one have a pi bond? Oh, remember my drawing did not show the formal product. Okay, so if we're going to push that a little bit more, that's not a reaction. Your lone pair comes in, attacks. I drew this way too flippin' large. That would effectively be your 1, 4. You could fix the hydrogen by removing the hydrogen with water. That's why the water was present. So your sulfur picks up that lone pair. Okay, we could pick up the hydrogen with our oxygen. Okay, and what we would have done is the formal 1, 4 addition. Right, 1, 2, 3, 4. We added something at the 1 and the 4 positions. What functional group have we made here? An E null or late, depending at what charge state you're referencing. Okay, the problem with that? They're unstable and they would revert to the ketone through that tautomerization. Okay? So again, the initial drawing that I set up was just to acknowledge where I wanted the chemistry to occur. I know it needs to happen there, which answer choice. So it's a locator, not an answer. Okay? Once I look at my answer choices, I can decide, do I need to go through a mechanism? The locator told me where to go. I only had one answer choice, match the locator. I don't need a mechanism because that's the only answer choice. If I had two answers that match that locator, absolutely right, I'm now stuck. I got to go through the whole mechanism. Does that make sense? Kind of makes sense?
Yeah.
Okay. Challenging because you're looking at a new nucleophile. But again, the point of how we've been discussing the content is not to memorize the reagents, but to focus on what the chemistry is and allow you to extrapolate to those larger questions. Questions about it? Did I record? I did record. Looking at that, the answer was exactly, why are you getting to the answer B? That's what your B is, the end result. We need to know your thought process to get to B. So what are you seeing that makes you go, B is the answer? Okay. All carbon, which I would push on a little bit more. Karina was going through and noting that the other three, well, let's be more creative. Nitrogen, nitrogen, oxygen. The three of these isn't just all carbon. What else do they have?
And they have electrophilic or holding carbon.
They have an electronegative element, right? Right. So is that all you saw and then said B? Or did you see anything else? Both answers are perfectly awesome. Hey, well, you started this with B, didn't you? Unless I've been shouting at the wrong person.
That's all I saw.
That's all you saw? Okay.
I think.
Which is fine. I would argue you probably saw more than that. You just aren't vocalizing it or realizing you've pushed that brain thought through. Right? So what we've vocalized so far is pure test-taking strategy. Okay? There's nothing else to this that says anything that you know anything about organic chem. Well, nitrogens and oxygens, I'll accept that one being electronegative, different from the carbon, perfectly valid for what we've got identified. You're saying the one thing that does not belong is B, so I'm going to pick that one. Okay? I think you know a whole lot more, and it just hasn't been articulated yet. So go for it, Karina, because I can tell you're dying.
Well, I think because of those electronegative elements, that there's an electrophilic atom nearby that would react with a nucleophilic addition.
Okay, so let's push on that a little bit. You're going through and saying because it's electronegative, I have an electrophilic atom nearby. Okay. In and of itself, I would argue that's nothing more than what we've already established, right? I know you didn't stop. Okay? And then you continued and said to the question, because remember, the question is also part of this. So if we're thinking about how we approach this question so far, right, and I'm not saying everybody did this, but what it looks like everybody did was they looked at the answer choices. And you started to piece through those. Okay? And there's a couple interesting reasons for that. Okay? I would potentially argue. Okay? The whole point of this class, what did we look at? We didn't just look at answers. In fact, we've rarely, if ever, looked at answers. Go back through and look at all of our lecture videos and recordings. How much time is actually devoted to what the answer actually is? The vast majority of our time is the process to get us to the answer. Right? But in that process, what have we always evaluated? The chemistry. The chemistry found where? In the structures. So your immediate leap is to go to the structures, which is good. Okay, but we do have to be careful using that sometimes. Okay? This question in particular is a perfect example where we should be a little bit careful. Because where do we see structures only? It's only in the answer choices. It's not given in the question. Which means you're basing your entire philosophy for answering this question by only looking at the answer choices. 75% of what you are looking at is wrong. So you're now spending time looking at wrong things to frame your answer selection. That is a questionable strategy. Does that make sense? Okay. In this particular case, it absolutely worked, so don't stress on it. Okay. But what you're basing it off of is test-taking strategy. So what I would like is a little bit more, where is truth? The truth for every question has to come from only one spot. The question stem itself. Okay. And what I find fascinating is you all look to structures. Okay. I'm going to say you look to structures. Maybe if they were words there, you would have read the question first. Okay. But we're all 18 and older, 17 and older. I don't know how old everybody is, but let's say at least 18 years. You've spent 18 years speaking the English language, and your number one place to start was not the English language? That's a little strange. Okay. But what have we also learned growing up through all of our elementary school? Oh, we hate word problems. We don't want to look at word problems. Use the words, leverage the information from the words, and get it into something that's useful for you. So if I want to run a nucleophilic addition, so what I want to start with is, what does the question give me? There's a whole bunch of words up there. Okay? One word I would argue is going to be really important there. I've got that least I need to identify. And then undergo a nucleophilic addition. Okay, what does that mean?
It's likely to go in a nucleophilic addition. It's
What is a nucleophile?
a thing that likes.
Okay, and so you're starting to use words now. You don't have to use
Donate
words.
Electrons to something.
Okay,
You got that.
so the nucleophile would likely be negative. What is addition?
Removal of a pi bond to make two sigma bonds.
Cool. Okay, so if we now consider that as truth information, we can start to see why potentially maybe some of these answer choices were placed there. If the first thing you're looking for is a loss of a pi bond, what's your answer choice?
Maybe C.
Maybe C, because
You don't see the pi bond.
the notation is changed in such a way. And if you're like, well, but that's awesome that you're saying, well, but that's fantastic. You've acknowledged you see something there that, number one, you did not tell me you saw 5 minutes ago. Okay? So when you see that CN, don't leave that as CN. What is it? Okay? And if you want to add lone pairs, that's fantastic. Do that too. That changes your interpretation and your ability to answer a question. Okay, and again, I might, well, but I got this one right. You got this one right. What about the next one? Okay? And in an exam, what we're trying to do is minimize your mistakes as much as possible. The more you do in your head, the more shafted you become with your answer choice. Okay? So make sure you get that clarifying information out there, because it is incredibly common to lose the triple bond when working with nitriles. Okay? So loss of a pi bond, damn, that doesn't help us. Okay, gain 2 sigma, it's not telling me what 2 sigma things I'm going to gain, so that's not particularly useful. But I do know that in the process of doing this addition, I have to react with a negative, which means the substrate, my answer, needs to have what? It needs to have a positive. Now I can go through and look at those answer choices and say which of those generates a positive. A, A, C, D. You said B.
I did not
Did
say
you?
B.
You didn't say B? Okay, that's fine.
I did not say that.
That's okay. It's a non-judgmental judgment. Okay, A, C, D. Why are A, C, D all generating a positive? They're connected to that electronegative element. So it ties back to that observation that you made earlier also. Does that make sense? Okay. Do you get what I'm trying to push at you? Track the information you have. Ideally, get rid of the word question and convert it into a language that you understand and can manipulate. Okay? And sometimes you may not know the words. Okay. If you're in that boat, fine. It's test-taking strategy. That's okay. Okay? But in practice, what we should be trying to do is get used to the patterns of always specifying that information so that when it comes to the exam, it's not oh, now what do I have to do? It's part of your ingrained nature to already write that information out. Does that make sense? Questions? And then, hell yeah, good job.
Could we act as a weak nuclear file for a 1-4?
This is why I was waiting for someone to say B. Okay, could B act as a weak nucleophile for a 1,4 addition? Okay, so there's a couple things I want to unpack within that. First, I just kind of want to get rid of the whole question because none of that is particularly relevant. So could it act, say it again, an electrophile for a 1,4? A nucleophile for a 1,4. Ooh, wow, no, did not expect that question. Not what I thought you were saying. So if we set up a 1,4, the 1,4, we've got our oxygen, we've got our carbon out here, right? These, if we're going to push language, are an alpha, beta. I don't know why I decided to go cursive there. Oh, because I had alpha and beta. Unsaturated ketone, which could be labeled actually as just a carbonyl. Okay, so you could see reference to that language. What we're talking about is that nucleophile attack. How do we make the alkene react?
You gotta.
One option was a catalyst. What kind of catalyst? I think I heard heat. Heat is not a catalyst. Heat is a condition. Acid. So we add H+. Hydrogen gets added to our least substitute. We form the more substituted carbocation, and now we could do a nucleophile, right? Okay. What other reagents could we do? You can't do base? Why can't you do base?
So are those hydrogens?
How does the alkene react? That is a non-polar pi bond. As a non-polar pi bond, the thing that is reactive is the pi bond itself. What is the pi bond itself?
Negative.
It is 2 electrons, also known as a negative. And if I bring a negative near hydroxide, what's going to happen? Nothing. They're going to repel away from each other. So hydroxide doesn't work in this case. I have to run with an acid catalyst. Okay, but I don't have to do an acid catalyst. We could do BH3THF, right? Followed by our sodium hydroxide and H2O2. Why did this react? There's no acid. Is the empty p orbital on our boron. That empty p orbital can accept electrons. Why is it reacting? To force the alkene to react, we have to add a strong acid or a strong electrophile. Those are our two conditions to force it to react. So, to your question, I'm going to be sort of rude. Is the alpha-beta unsaturated ketone a strong enough electrophile to force that reaction to happen? And now I'll be less of a jerk. I genuinely don't know. Okay? I would side with you. I would say no. It's not polar enough to force that chemistry to happen. Okay? We would need a stronger electrophile to force that. That's where we're bringing our boron or our mercuries. We need something more active. Could you make it happen? I don't know. If you could make it happen, what might you be able to do? Yeah, you could attach your name to it. Okay? So if you could come up with the conditions to force the alkene to react with that, that could be a named reaction. Okay? It may have already been tested, but yeah, I would argue the alkene is not nucleophilic enough on its own, nor is the alpha-beta unsaturated ketone electrophilic enough on its own to allow that reaction to happen to any great extent. That was a nice curveball. Where I thought you were going was, if we look at the resonance structure, don't I have a negative? Why can't that act as a nucleophile? That's a relatively weak contributor to the resonance of that structure, because those carbons have the equal electronegativity. If we go through and shift to a carbonyl, the carbonyl is going to give me that negative oxygen and my positive carbon to a much larger extent, because the oxygen is polarizing that bond. Questions? Okay, good job. So if we record the video, or rewind the video like 10 minutes, we get this giant lecture about, don't look at the answer choices. The answer choices are all wrong. And unfortunately, what are we going to have to do for this question? We're going to have to spend a lot of time looking at the answer choices. But again, before we dig into the answer choices, we should identify the information that we know to be true. What information do we know to be true? I would argue there's two things. What is racemic? Okay. Blend of enantiomers. I like your statement of not optically active, but it's not technically going to work. Is this optically active? This structure right here? Is it a racemic? This one's not going to be racemic. Okay, so to be racemic, we have to have more than one enantiomer. Okay, but I would argue the blend isn't going to be perfect either. It's not a blend, it's 50-50. Okay, or 1-to-1. Okay, so we are getting two products out of the course of this reaction. Okay. What else should we be identifying as truth from our question? This one I would argue is trickier. That not is going to be pretty critical as well when we go through and evaluate our answers. Does that make sense? Okay. You guys, right here. This row, column, whatever you want to look at.
A, B.
Yeah, do A. Y'all get to do B. And y'all get to do C. Predict out the products. You can do it up on the board. That's perfectly all right. Did not consider that, but you don't have to do it on the boards if you really don't want to. I'm not going to draw those ones out because it's ultimately going to be very similar to what I'm going to draw out for answer choice C. So when we go through and look at our overall reactions with this, we've got our starting material, we have our active nucleophile, and then that nucleophile goes in and reacts, right? What does it react with? Electrophile is too broad of a term. There is that possibility for it going through and reacting with the hydrogen. Here we're trying to run that nucleophile addition. What is it reacting with? And for everybody struggled with this question, for the record. Okay, it's reacting with the carbon. What is it reacting with on the carbon? The positive charge, right? Where is the positive charge? In the p orbital, which means when that carbon comes in and attacks, it could come in and attack from on top. Stupid thing, do what I want. In which case, I should get a wedge CH3, and where should my oxygen be? I already just realized I drew this wrong. It should be dashed. Did a couple people already notice why it's wrong? Such jerks. Okay, and why is this now going to be wrong? There's no physical way to draw that structure. That you can't make a model look like that. Okay, so if we were going to fix that, so some people were saying something else, which makes me feel a little better. We could have the CH3, we could have our dash to our oxygen, and then we could have the rest of my carbon structure here. Oops. So this has to do with the orientation of those groups. Your two solids have to form a triangle, and the wedge and the dash have to form a triangle, and they must point to each other. If we look at how I initially drew this out, that drawing physically can't exist. It's not going to work. Okay? We can understand it, use it to understand how we positioned it, but it physically doesn't work. Okay? Or technically, and we could have it come in and react on the bottom, in which case, where's the CH3?
Wedged. The oxygen is dashed.
Okay. So thankfully, we don't have verbal tests.
Yeah.
Because I would argue the one with the lines here would be dashed and the solid one would be wedged, but that's okay. Okay? And so we get those two possible products. Okay? So we get two products. So therefore, we have two products. We would now say that all of our answer choices, because if we look at the rest of the boards, all of them came out with two products. So therefore, all of them form racemic mixtures. Well, that should scream problematic. Why? There's literally no answer that would cover that. Okay? If that's the boat that you fall in and you're like, well, dang, nothing works, what's your response on the exam? There's two really good responses. One of them is correct, but it should happen after the first. So moving on, absolutely. You're missing something, move on, come back to it later and hope something shifts and allows you to figure it out. But before you do that, you should make sure that the reason you're missing something is because it's your fault, not the exam. How do you verify that? You need to ask. You'd raise your hand and be like, Mike, did you screw up this question? Okay. And I will, full disclosure, say you need to give me time because I'm going to have to sit down and look at this and make sure that there wasn't something that I missed inadvertently that screwed this whole question up. And I will tell you to move on. Okay? Because you don't want to sit there and spin your wheels on a question that has an error. Okay? If you can prevent it. Okay? Eventually what'll happen is I will come back to you and I will be sorry. There is no mistake. This one is valid. Which now means you have to more closely evaluate what you went through and did. If you drew out all the products, you could go through your system and evaluate. Our rules said we needed 2 products, but is that the only thing that our truth said? It's not just that we have 2 products, it's that of enantiomers. How do I know I have enantiomers? I have a stereo center, and we're looking at non-superimposable mirror images. Okay, so the easiest place to start would be looking for that stereo center. If we go through and look at the boards, hopefully what we'll see on the boards is they all have stereo centers. So the boards are all going to be a racemic mixture of products. The question is very specifically looking for not. At this point, we could make the gut punch and just say, well, if I know the other 2 are fine, then I'm just going to say it's C and hope and move on. Right? But if we take a closer look at C, we could try and deal with the non-superimposable mirror images, or we follow what Kazai was saying, which was a fantastic idea. Let's take a look for a stereo center first. Do I have a stereo center? No, this is a CH3 and a CH3. I can't differentiate those 2, which means no stereo center. Do I still get 2 products? It's kind of a weird statement to make. I would kind of say yes, there's 2 ways to make a product, but the products that come out are identical.
Put a hat on one of the methyl groups, and it's the only way to know.
You got to be careful with that, particularly for this case. You're like, oh yeah, they are mirror images because one has a hat. So be careful with that. I've definitely been bitten by that one. Not that I've drawn hats on them, but other markers. What's that? Like literally, you go to your CH3 and you draw a little hat on it. Like this way, I can tell a difference between it. That's literally what she's saying. Which isn't bad. Like, I would do the same thing. Like, can I differentiate these things? But that's where you have to be careful, is you know, oh yeah, now I can tell a difference. You can only tell a difference because you added the hat. So you got to be careful. So C encounters, yes, some interesting potential problems with it because that bond, well, actually, let's push on that. So let's get rid of all of that. And let's go back to really what you wanted to ask on this. So if you came back during the test and said, this is what I think C is going to go through and do, you will open a can of worms, and what I'll say is I'll announce to the class, only do nucleophile addition and adjust. Okay. So why do you think C is going to do something else?
It's lithium's properties, whatever we learned that CH3, lithium, that carbon would act as a base instead of a nucleophile because of the
That bond is so incredibly polar that carbon's going to pick up such a large negative charge that it's more than likely going to act as a base instead of as a nucleophile. And since we have the potential for acidic hydrogens, where are the acidic hydrogens?
the alpha, either left or right. This would be.
We have alpha hydrogens available. That base could theoretically come in and remove those hydrogens. Okay? As soon as you start that process, if you've already done A and B and you move into C and you start doing that, that would be a question, I would argue. Okay? Because now it's not just a simple, hey, I just add and neutralize. It's now I have to remove that, and now what happens?
It's added back.
It could be added back.
You get a enolate.
And what could the enolate potentially do? Yes, resonance, or you could get potentially a nucleophile addition doing aldol type chemistry. Okay, that aldol chemistry is going to push through a whole bunch of other stuff. That's a bunch of other chemistry. There's a lot of things that go into that secondary question that aren't being involved at all in those first 2 answer choices, which is why I would be like, this is what's supposed to happen, and I feel like this is going to go down a really bad path. should I actually chase it?
But then you would get like four products. So then it wouldn't be,
And if you're going to continue to chase it, you push all the way through that, how many chiral centers are you going to have?
it's only gonna be,
It's going to be 0. You're under conditions where you would actually eliminate as well. So you'd do the aldol followed by the condensation. You'd lose the chiral atom and you'd be right back at the correct answer, but after having spent 10 minutes to get there.
you're doing the correct chemistry. Alright.
Yep. Kind of makes sense? Good work. You got them? What's the next one? Very common format for testing questions. I would argue it also is kind of boring and very repetitive. Within these types of questions, there is no need to look at your answer choices because you're just being asked what's the product. Okay? So that when you look at this, what do you see? Not you, Tyler, because you already said it, hopefully quietly enough nobody else answers. What do you see? We've got a leaving group. Which isn't bad. Okay, I would argue if you're looking at this and you see a good leaving group, that's fine. What you're committing to is drawing out the full mechanism for this. And hopefully at some point through this process, you will draw a structure that helps click. Hopefully you draw this structure and all of a sudden something clicks and you go, oh, I know. Some point through your process you draw that out and you get that. Does anything click yet? Okay. I like where you're going. I'm not sure I understood at all what you said, which makes me think that was wrong. Okay. That yes, this is a named reaction. This is one that I would probably commit to memorization. Those first 2 steps get you to this structure. This structure is important. How to get through those first 2 steps absolutely is valid and follows standard chemistry that you should be able to navigate. But reacting the yelid with step 3 is not a straightforward mechanism, and that thing becomes ugly fast. That's where I would commit that part to memory, so that if you are seeing this sequence of reagents, and actually I would group the aldehyde within that, okay? Or you're seeing this structure, what you should be having memorized is this is the Wittig reaction, okay? The cheat that I've told you for the Wittig reaction, particularly in a scenario where all you're asked to do is to predict the product, is to take your aldehyde, stretch, actually you don't even have to stretch the aldehyde on this. I think I'm thinking of the aldol. So you take your aldehyde, you delete the oxygen, and then you replace, replace it. Keep getting isits in there. I think I've got it right though. With the carbon of your alkyl halide. Okay? That's your cheat. You just do that exchange.
Does it have to be an aldehyde?
It can be a ketone as well. Okay, you're looking at aldehydes or ketones. So cool. Is that the only possible product? Okay.
Got a different oxygen.
So there is a different oxygen. I believe what you're referencing is down here. but that's not a carbonyl, so that's not going to have something for us to worry about. That's going to change patterns behind how this reacts, and we'll talk about that here in a second. There is another product. What is the other product? What's that? Nope. This is the other product. What's the relationship between those two structures? These are cis and trans. Okay. Which one is the correct product? Okay, so here we encounter a couple interesting lines. So one response I think is a fantastic response. Whichever one of these is in your multiple choice is the correct answer. Okay. What if both are there?
The trans, because it's less sterically diverse.
Okay, and so this is where the Wittig reaction actually has some interesting dynamics associated with it that we didn't go over in lecture. It's still a mechanism that's under study. Depending on the substitution pattern of your nucleophile and your electrophile, you can change whether you get cis or trans. Okay? So the reaction can be tuned to force one product versus the other. Okay? That tuning requires lots of advanced knowledge. Do you have that lots of advanced knowledge? No. So one or the other, or both. Those are your potential answer choices. You are not expected to look at the starting material and say, that one's going to produce the cis product, that one's going to produce the trans. That's not part of your content realm. Your content realm is that I know it's going to swap out, I know I'm going to form the alkene, and then there's this possibility of getting cis or trans or both as possible products. Okay, did you get a picture already? Okay, did anybody else want the picture before I delete it all? We good? Is it just not working? Okay. So when we're good, I'll delete it all and we can look at our answer choices. When you go through and look at the answer choices, you will see that both these structures are there. That was a typo on my part, okay, when writing the question, because I was trying to come up different ways to permutate it, and I permutated it incorrectly and just had both answer choices there without including the both of these answers are valid statement. Okay, which is why, now we're good? Which is why, for this particular question, it says that there's a typo and you should select all answers that apply. Does that make sense? Okay. One thing that I would point out is look at all of the answers. So 2 are correct. Is it obvious to you right away which 2? Okay. So some people are psycho and can see it. Okay. Other people don't see it. It's going to take a little bit of processing to find all of those pieces and where all those things come together and come into alignment. Okay. So this is one of those structural things that you end up being, don't worry about it, I'll take care of it. Or you can keep hiding it. That you're responsible for in the grand scheme within OCHEM. Okay. So with this question, draw out your correct answer. Recognize cis and trans. You can just make yourself a note and then go through and look at your answer choices. Okay, and as you navigate them, this is a case where I would cross off answer choices, being like, no, that's not right. That's not right. And zero that in. Kind of make sense? Okay. With that, we're done.